Hi everyone, it's Clara Barker here, and I'm back with another one of my science chats. So in these chats, basically, I just have a chat. I have a chat with a friend of mine who is in science or engineering in the STEM fields, basically, who I really get on with, that I really enjoy chatting to, and also it gives me a really good opportunity to learn as well. I might forget what I've learned, but I do try and learn. And today's guest, Shazeaa Ishmael, has taught me so much about quantum physics in the past. I've forgotten a lot of it, so that's great. I can re-ask those questions. But yeah, it's really good to be able to talk to Shazeaa. And then I'm also, so it's a great opportunity. We haven't caught up in a long time, but we do work in the same department, so we know each other quite well. That'll probably be obvious. I will say that Shazeaa's got a Twitter, so I'll put the link below so you can follow her, and don't forget to subscribe and like to this. But with that, we'll go to the intro, and then we'll welcome Shazeaa. So, hello, Shazeaa.
Hello, Clara. Thank you for having me on your podcast. I'm so excited to be here. I repeat, a year and a half later.
I know. So for anyone listening, basically, Shazeaa offered to be my guinea pig a year and a half ago when I thought that filming in person. So I set up a camera and we did the sound and we filmed it in my lab, but it was really noisy. I had one video, the lighting was terrible. Basically, the content was amazing, but it wasn't going to look great. So I'm really, really pleased that you were willing to come back and do it again and talk about all that stuff again.
You've had some really good guests. I feel as though a high standard has been set. It's just going to be me waffling about physics.
That's perfectly... Well, that's what we want. We want people to waffle. Waffle's the wrong word, but we want people to talk about their science. That's what I want this to be. I want it to be an opportunity for me to learn stuff. And it's kind of interesting because I've had Andrew and Clara on, and because I sort of knew a little bit about what they were doing, but not loads, I was able to ask questions. With Izzy, I feel like I don't know quite as much of her area, so sometimes I don't know. I'm not sure what the balance is, but I'm sure sometimes I ask questions because it's like, I need to know this and I want to know this, and other times it's just purely interest. And so I should say with that, who are you? What do you do?
So my name is Shazeaa Ishmael. I am a PhD student at the University of Oxford in the materials department. So I work with Clara. My PhD project is using defects in diamonds to network them together to become a quantum computer eventually. So it's a lot of buzzwords for sitting in a dark room a lot of the time, basically. Me and Clara actually met through the Equality and Diversity Committee in the department, and we've done quite a lot of projects together and been to loads of conferences and stuff together. So that's also a lot of what I do as well, not just science at Oxford.
Yeah, no, it's like you say, I think it's that important line, and we talk so much, and when we're in the department and we're able to see each other, you're the person that I know I can go to, and we can have a really good chat about what needs to change and what's working and what isn't.
Many a debrief about things happening in the department or in Oxford.
Oxford in general, materials isn't perfect, but I'd say that I felt really comfortable in the materials department in Oxford. I feel it's a really good place to be, and like I say, it's not perfect, but they're also willing to listen. And that's a really good thing. And I'd say the current head, Angus, is definitely willing to listen to stuff, and Patrick and Peter, the previous ones as well, they've always been willing to listen, which is nice. I know I can always bend their ear.
I think they're also committed to do something wrong and what can we do differently as well. Whereas a lot in Oxford, you get a lot of talk and not much action. And I think materials is kind of on the better side of that compared to other departments. I mean, the standard's pretty low, but
yeah, that's true. And one thing that I would say is that I think when we have a lot of these equality and diversity, when we're talking about improving things, we'll talk about this a little bit more sort of towards the end, but when we're talking about equality and diversity, often we're saying we want to change the face of sort of science to make it more diverse, to make it more open. But that doesn't mean that we're saying that the stereotypical old white straight grey-haired men have to go. No, actually, like Angus and co are
Our heads
fantastic
department are
allies.
white men.
Yeah, and they've all been.
Most professors are white men in the department as well.
Well, yeah. I mean, there is that. But this is the point. We need those on board because that's how things will change. And it's great to have people who I count as really strong allies in the department. Yeah. So we can go into that. We may well do. But let's start with your science. So what do you do? What do you do in the department?
So I don't know how to start this. Okay.
Do the elevator pitch. Start with the elevator pitch.
So basically, the work that I'm doing is a lot of like practical experiments or building equipment that will hopefully lead to a viable quantum computer. So quantum computing is basically almost a different type of computer completely to what we currently use. At the moment, what we call classical computing, all data is like stored in the binary, so 1 or 0. So you have these like magnetic switches and stuff, and everyone kind of knows like the basics of how binary works. But quantum computer sort of enhances or uses the like quantum weirdness of like how things can be 1 and 0 at the same time. And basically it's a completely different way of computing essentially. So you don't just have to be 1 or 0, you can be 1 and 0 at the same time. So you have infinitely more bits or states in which to like store data, and the way you would carry out algorithms or problem solving is completely different as well. So it's not necessarily like a better computer, it's almost like a completely different type of computing. It needs completely different networks, completely different materials. So yeah, I know Andrew was on your podcast like a few weeks ago, or ages ago maybe at this point, and he talks about quantum materials and things they could be used for. So that's basically what my project is as well, in terms of like building the equipment to control those materials. And the material that I happen to look at is diamond. So diamond's quite like a not necessarily new quantum material, but we've only just been able to grow like really high quality diamond that can be used for quantum applications. We actually look at imperfections in the diamond. So I look at the defect called a nitrogen vacancy center. So it's got a nitrogen in the place of a carbon atom in the diamond lattice, and then it's got a vacancy next to it. And this defect has lots of unique properties that mean it's ideal to be the building block of a quantum computer. So all of my work is to control the defect in certain ways so it can be used eventually for different quantum applications.
And it is mind blowing.
Or do like some slides or like a whiteboard somewhere.
I should have set that up. Yeah, it's baffling. So what you're saying is basically the way that we store data at the moment, this binary, this ones and zeros, and that's great for now. But
there's still a lot of limitations. So even really like simple simulations of like a 2-atom problem, you have to make like so many assumptions, because what's inherently like a quantum problem, you don't have a quantum basis in which to solve it. So you're solving in a binary system. So you kind of have to make a lot of assumptions that aren't necessarily like accurate. So you're kind of not getting accurate measurements of your simulations, I suppose. The one like analogy that people always use to kind of illustrate the power of a quantum computer is like if you were in a library and you're looking for like a certain word in these like millions of books that you have, a classical computer would look through every single book individually to look for this one word you're looking for. Okay. But a quantum computer would look through all the books at the same time, find that word, so you can do things like a lot quicker, but in a completely different way, essentially.
That's amazing. So I think, that's sort of a key concept, isn't it? That there's more processing power, as it were, like you say, you can, and the truth is that as we move on with our scientific experiments and we're trying to design more things, it takes an awful lot of processing power to do these things. I know that we have people who are running simulations in plasmas, and I think they leave their computers running for 3 days, and they're high power computers, and you're saying that we can do this a fair bit faster.
Yeah, so we're not at that stage yet where a quantum computer surpasses like supercomputer powers at the moment, because we haven't got enough qubits or like quantum bits all working together to make it significantly better than like a regular computer or a supercomputer. But they're hoping to get there essentially. Like IBM have got like 50 qubits online that you can like go and code in little things and run little experiments and things like that. And there was obviously, I mean, like quantum's such a buzzword at the moment. There was a paper last year from Google. There was one earlier in the year that talked about like quantum, I hate using that word, quantum supremacy, but how like quantum computers are better than classical computers and things like that.
I think that's interesting. So I did a little video on. Have I done it? No, I haven't. It's coming up a little, okay. But it will be out by the time we release this, actually, on fusion energy. And so fusion energy is something that we're talking about and we're trying to work on. And the truth of the matter is, at the moment, we're just breaking even with creating fusion energy. We're years and years, and we're talking tens of years away from actually sort of getting results from the new fusion generator in ITER. But there's the chance that it'll be this big, huge breakthrough. And I think it's the same with quantum computing. We're working towards it because we want this breakthrough. Is that right?
It's interesting how like quantum computing and nuclear fusion are always compared as these two like scientific ideas that are like just on the cusp, like we're nearly there, like a bit more research. Because when I was at school, nuclear fusion was like the next best thing. This was probably like 10, 12 years ago now. They were like, oh, nuclear fusion is going to be amazing. We had someone from Rutherford come to our school and talk to us about how good it was going to be, and it's still like not quite there. Yeah, and not that we're like overselling quantum computing, but I think there was a lot of hype with nuclear fusion, and the way that scientists talk about quantum computing, they're kind of careful not to oversell it too much. Like as to where we currently are now and where we're planning to be, there's still like a long way to go, and I think people are quite realistic about how far away we actually are from having like everyone using quantum computers. I don't think it's ever really going to happen. Everyone's going to have a quantum computer in their pocket or anything like that.
Yeah. Actually, I've just been realizing, like, we were talking. I was talking about fusion. I brought fusion up, and I realized that a lot of the stuff with plasmas and with things like CERN is the calculations, how long it takes to do the calculations. Ironically, if we had the quantum computers, then we'd be able to develop fusion energy a little bit faster.
But, what is the like rate limiting step in fusion at the moment?
So the new system that they're going to build in ITER, which is they've just started building ITER in France, and that, I mean, they're not going to have started running experiments on that until 2035. So they hope to have some results by 2040. It's the size. Yeah. And the reason that I've talked about fusion, so I can't say that I'm an expert on it, but the reason that I was talking about it is because we use superconducting magnets to bend the plasma, to keep the plasma away from the walls, because otherwise the walls melt. And so part of it is the thing with ITER, and the next thing they're going to do with the Large Hadron Collider is increase the superconductors. So when I'm talking about increase the superconductors, I'm talking about increasing the magnetic field that they can generate, so that we can confine the plasma even more. So it's sort of a superconductor thing, but it's not completely our fault. But that's it's one part of the puzzle anyway. There are others.
I think also with so many of these like contemporary science problems we're trying to solve, it's the engineering of like all these different disciplines coming together.
Yeah.
So like my training's actually in physics. Like I've got physics undergraduate, but I work in the materials department, and actually a lot of my PhD in kind of engineering based, like problem solving. And even though I'm like building, I actually do a lot of like Confocal Microscope building. So I do a lot of optics and like laser lining and things like that, as well as sort of like materials processing and some like fabrication work and some like microwave engineering. It's a lot of these different disciplines all coming together, and the work that I'm doing is actually funded by the Quantum Computing and Simulation Hub, which is got like government money to fund it.
Okay.
And we have all these different like work packages, and there's people who do like so many different things like optics, photonics, like people writing code and all these different things all like coming together to work on this one project. And it sounds quite similar to fusion. It's all these different departments all like coming together essentially to get this one thing to work. You can't just be an island and hope your experiment works, as it were. It really relies on collaboration.
Yeah, so one of the conversations I've had before is with Dr. Clara Nellis of who works at CERN, and what was interesting there was we were talking about the publishing of null data or experiments that failed. Like in the particle physics world, you're encouraged to publish all results because that moves the field forward. Whereas I know in my own particular areas in the past, if you've got null results, you don't publish it. And you'll be talking to a group and you'll find out that they found that out 4 years ago, but everyone wants to get their name on the paper, and so they want to get it out first. So I thought that was kind of interesting. And I there was a TED talk. So I did a TEDx London Women talk in 2018, and one of the other speakers, oh my goodness, I think she was high up at ESA or head of ESA or something, so the European Space Agency. And she was saying that, all the countries around the world are arguing with each other, and yet when it comes to space and looking at the data, they share everything and they're talking to each other, and they're looking at the planet, and they're looking at the, whether it's sort of issues that are happening because of the weather, the environment and things like that. They're actually working together, even though politically on the news, all you ever hear about them is, them arguing with each other. It's something
actually in science that I really had to struggle to get my head around, how like some things are really collaborative and then some things really aren't. And like, maybe this is like drifting too much away from actual science, but I think it's important because no one talks about it enough.
Yeah.
It's how competitive science is. Like right now, as a fourth year PhD, I'm supposed to be like writing up my thesis, like applying for postdocs, or I'm not doing that. Writing up papers and things. But actually, and everyone wants to hire a postdoc that's got all these like first author papers, and everyone wants to publish a paper that's like the next big thing, and we're all like selling our science as like amazing. But why aren't we publishing the data that hasn't worked as well? Why is it only kept for someone's thesis or kept in a lab book?
I honestly,
also the idea of like only the first author being important on the paper, when literally you'll have like 10, 50 on like on the LIGO papers, there was like thousands of authors on it.
Yeah.
Like all of these people, all of their work has been important, even if it's just been like a conversation you've had that's been like a bit of like, coding or simulations for you. That's all like important on paper. And there's like, not every scientist is gonna have a first author paper, but it doesn't mean they're not a good scientist or a good like group member to have, or a good addition to your team, or a positive addition to your team. That's why I think it's interesting in science how we like value worth of scientists and how we value like our research, as it were. Like it's all got to fit into these like 4-page papers that get in a journal that's got to have a certain impact factor. But all of that is incredibly biased and all these other reasons why it's not accurate.
Yeah.
It doesn't really show you like how good or bad that person is as a scientist, or like how hard they've worked. Maybe it hasn't panned out for them, or like what else happened to them, what's been in the lab, or how much time they've spent like helping everyone else out in the lab, or how much time they spent organizing the lab, or all of these things that are still important to a research group. Don't necessarily have these like measurable research outcomes that everyone wants to see.
No.
When I started my PhD, that was really like weird or difficult for me to like get my head around.
I think especially if you're working on cutting edge science, the chance of it actually working is much slimmer than it not working. And so I was working with types of equipment which were experimental, which were new, and I think they've improved since. And that meant that there was a lot more null data. That I did a lot of experiments, but the amount that I could actually publish was very, very limited, because it's all about, you've got to have the good results. And I know full well, I'm looking at papers now and I'm thinking, I did a lot of this work before, and if I'd have published those null results, I would have got that citation. But because the thing is not publishing null results or negative results, that's why. And so it does mean that you've got to be lucky with the results to a huge degree. Like,
even just lucky with writing a paper sometimes, and who your referees are and which journal you submit it to. Like, I didn't realize how long the process was to like submit something to a journal, get published. I just feel like no one told me that at undergrad. They were like, just like publish a paper and it'll be fine. But like, no one told me it could be like a year of revisions, or like all these other things would come into play. And
it's a long process. And you talked about impact factor as well. Like, you know, the sort of materials that I'm publishing or talking about are doing, they're in smaller impact journals, but the people that are going to read them are going to read them in those journals, and they're just not sexy data. They're not sexy. You can get it in Nature or Science if you include certain keywords, buzzwords, but you know, for the nuts and bolts of sort of material science, they'll get read a lot, but not in that high impact factor journal. It's going to be a different one. So yeah. So just coming back to quantum, the quantum world, quantum computing. So we already talked about the fact that it's got this huge amount of capability in terms of processing data, potential processing power. What does that mean for? And we talked about sort of being able to model experiments and things like that. But what about for everyday people? Is there any benefit? Is there anything that could spin out that could be used for, people?
So I think it's very similar to the way that computers were introduced into like our everyday lives.
Okay.
Like initially, kind of research facilities were the first people to have like computers at all.
Yeah.
And then slowly they kind of spread out to everyone else now carrying them in their pockets, essentially.
Yeah.
And I don't think there is going to be a need for everyone to like carry a quantum computer in their phone or anything like that at all. I don't think we'll get down to a stage where like they're going to be that small anytime soon at all.
Yeah.
So I think it will just be like, again, like research facilities. I mean, the military are very involved in quantum computing as well. They're very interested in it. There'll be the people who are like investing huge amounts of money into the research at the moment and benefiting from it like initially. I don't really know what kind of timescales we can expect like everyone to be carrying a quantum computer or anything like that. I mean, I already have a quantum computer, and they have like a number of qubits already entangled together that you can access and things like that. But there's lots of different groups and people across the world working on it as well. So like it is going to happen at some point, and it is going to be influencing research or the military or like all these kind of things, but maybe just not on like the day-to-day level anytime soon.
Why is it that the military are interested in it though?
I guess just having that extra, I suppose. I don't really know. I honestly don't know like why they were interested in it. Maybe like cut this bit out. So I don't know what the reason is.
No, well,
like in America, they've like massively invested in like the research that's happening there, and I think even here as well.
Okay, because my thought, I
think it's things like tracking and security as well.
Security, that's what I was thinking. Yeah.
So like quantum cryptography is something that like banks and stuff are interested in as well. So keeping our data secure.
Yeah.
And also the issue comes up is like who then has that power as well, because once you have a quantum computer, you can hack like any current encrypted system that we are currently using, because your computer is just like so much more powerful. So who's going to have access to that knowledge and that data and that power essentially is, I think, a cause for concern. Which
Mark
is probably
Zuckerberg, do it for. Right. Okay. So that's interesting. I like the security aspect. So, is it harder to get data without the? Oh, how does it? How could it improve security?
How does quantum photography work? This is not my area of expertise, like at all. Like, I'm
That's
not
fine.
a
Yeah. Sorry.
theoretical like quantum scientist, like at all. So anyone is like free to correct me or anything.
If you don't want to
But I
talk
think,
about that, I'm poking out there, so you don't have to
yeah,
answer.
maybe I'll try and say something. It doesn't make any sense, so you can just kind of cut it out later. But I think the way that like kind of basic quantum photography would work is that you could tell really easily if somebody was eavesdropping on your channel.
Oh, okay.
Because of like how you're interpreting the data that you've received. I think that's the reason. I'm not telling.
No, that's
I
cool.
do know that like quantum photography is like something that finance, like banking, security, they're all interested, and like now data's kind of become the new like cash, as it were, or the new like power, as it were. How we store that and how we process that is got to catch up as well with how important data is. So that's kind of, I guess, another reason why quantum computers are interesting to a lot of people.
Okay. No, that's cool. So, I mean, hopefully, maybe something a little bit that is more closely related to your research. But so, and bear in mind, like I say, I do not have a physics background, but we're talking about quantum, so I feel like the whole thing with quantum is we don't know what the data is. So, how are you actually measuring whether these things are working? How do you know whether they're working? I sort of feel like observing quantum information, I feel like it's not supposed to be observed, right?
Okay, so if we think about exactly what I'm doing in my research, basically what I'm doing is looking at these defects in diamond that when you shine green light on them, they emit red photons. Okay. And the amount of red photons they emit will indicate which spin state that defect is in. And that spin state essentially is analogous to the kind of 1 and 0 of a classical bit. You can be both 1 and 0 at the same time. So basically what you'll have like kind of two separate qubits or two separate defects in different pieces of diamond, and you'll subject them to a number of excitations of optical and like microwave range essentially. And they'll emit photons, and you'll be like collecting those photons in a way where you can't tell which quantum bit has emitted which photons. And when you collect two sequential photons, those two qubits will be entangled and they'll be acting as one. And you essentially could then perform a quantum computing algorithm on that entangled state, and you'd be collecting photons and things like that.
Oh, that's cool. So
you're not directly measuring your individual qubits. You're kind of measuring the emissions of those qubits, but you can't tell what qubit's emitting what because they're all behaving as one state essentially. So you can't cool. like directly say, okay, this qubit's doing exactly this, because it does kind of defy the laws of quantum mechanics essentially. So you kind of have to work around that.
It's good that you can, because like I say, I don't know, like say my physics isn't great, but I just had this idea that, as soon as we observe it, we don't know what it is, and so we couldn't look at the data. And I'm thinking, well, if I'm going to be storing my bank details in a quantum computer, I want to make sure that, the money that I put in is the money that comes out. Well, no, if it goes up a little bit, that'd be fine. I mean,
interest rates are really low at the moment, so,
So is my bank account balance, unfortunately. I am not making the most of that. Oxford rent isn't cheap. Yeah, so in the day-to-day in the lab, you basically said that you're shining lasers at diamonds. Is that right? So what's the setup for that? What's your sort of typical experiment look like?
So we use spin in our lab as laser safety officer for the department.
I
So
might
you've
have
seen
been.
like all of our lasers on and hopefully safely put together. So I basically had to build what's called a confocal microscope,
Yep.
which is a bit like a wide field microscope where you just have like a white light source, or you have like a light source and you just see like one image
Yep.
of like whatever you're looking at. Basically, what a confocal microscope does is it got a pinhole on the collection arm of the light reflection on the surface, so it blocks out all the out of focus light.
Yep.
You're like basically the hole you're looking through is really tiny.
Yeah.
You just would scan it across your sample. You can get like quite a high diffraction limited resolution image of what you're trying to look at. So I'll be looking at basically a chunk of diamond that's got defects in certain locations. I'll be looking for bright spots in my image, and they'd be my defects that I would then be collecting red photons from.
Oh wow!
So it's basically like an optical table with loads of different optics on it, and some green laser light that you might see, and then like a dark covered collection that goes to a screen, and then you're basically looking for like bright spots on the screen. And I also set up a system so I can control the spin state of the defect. So you're controlling how much red light your individual defects are emitting. So you'd be looking at kind of like the individual counts from one defect. And at a certain point, you'd look for like a dip in those defects and like a peak. And yeah, it's just looking at a screen and waiting for the line to do the right thing.
Unfortunately, yes, that sounds about right.
It's like all of science is looking at a screen and waiting for something to appear, I feel like. So much of my time is just doing that.
So much of my time. Yeah, no, I'm yeah. Looking at a screen and trying to make it do what you want it to do. But know that it's doing it on its own and not just because you forced it in some way. So, and how are you? Oh, sorry.
I am actually forcing it to behave in a way I want it to. So
yes.
I will be like applying like either a microwave field or a magnetic field to control these defects, and to change their spin properties.
Yeah.
And I'll be like examining those spin properties by looking at the photon emission from that defect. So I'm purposefully like causing changes to the defect.
Yeah, that's legitimate science. I'm sort of talking about when you take a graph and you're like, I'm reading it this way by putting it through this filter so that it says what I want it to say. Data manipulation is what I'm talking about. You're doing experiments. That's legitimate. That's above board. And with these diamonds, so are you putting the defects in there, or are they naturally occurring?
So we actually do both. Okay. The diamond that I use is not a diamond that's mined in the ground. Yep. It's diamond that's grown in a laboratory.
Yep.
Using a process called chemical vapor deposition, which essentially is where you create a plasma of like hydrocarbon gas and you cause the diamond to grow in like really thin layers.
Yep.
Kind of similar, not similar how you use into deposition at all, but you just grow layers of diamond off each other. But you get this really like high quality, really pure diamond that doesn't have many defects in it.
Yeah.
Initially, but like the nitrogen vacancy center does occur naturally because there's nitrogen in the air, and that can become incorporated into the diamond as it's growing, both in the ground and in a lab.
Okay.
But normally you want to have your defects in specific locations. So you can either use a process called ion implantation, where you basically bombard the surface of like accelerated nitrogen atoms, and then you have these NV centers in your diamond, like in the surface of it. But a lot of what our group is also doing is developing this process called laser writing of defects as well. Some of the papers that have been published by the fundamental materials group in Oxford has been on that work. So we're using like a high-powered laser to write defects at really specific locations. So you can literally have like an array of defects with like a few hundred nanometers accuracy as to where each defect is, rather than having to like search through your diamond for like a really nice defect that's behaving well, that's doing what you expect it to. You can literally write one into the location that you want it to be. That's not work. That's like what the group's doing, not necessarily me, but we do talk about it quite a lot. It's quite cool.
Yeah, no, I think that's really cool. And that's it, isn't it? It's so you've got members of the group that are sort of making these materials, and then you've got people that are putting the defects in so that they're where you want them, and then you can program what the defect's gonna. You can control the spin of the defects, and so you're looking at all the different aspects within your group, which is really cool.
With collaborators as well. So it's not just our group that does all the work. There's a group in engineering doing some of that work as well.
Yeah,
groups in Warwick and Strathclyde and Cambridge as well. So it's a really national project, national projects that we're working on.
It's interesting because we were talking before about the lack of collaboration, but actually we're seeing more and more.
I think you have to, you just can't do the stuff that we're doing, from growing diamond to putting in defects and do optical characterization that I'm doing to all these other things. You just need to have this knowledge that I just can't do it in one group. It's just too much work.
It really is. And actually I'd say it's interesting that we're talking about it before, because I'd say that the funding bodies are actually encouraging, they're more likely to give you funding if it's a collaborative project. So you're forcing that collaboration. And I don't see that as a bad thing. When I'm saying forcing collaboration, I'm saying you're making people, you're saying, we'll give you money as long as you're working together. And that's no bad thing at all.
It also means you're sharing what's worked really well and what hasn't worked well. I think more directly rather than having to publish papers. Because the group that I did my master's project in is now the group we collaborate with. So I kind of went there and had to do everything and then brought it to Oxford essentially. So that in itself has just bred more collaboration as well.
That's cool. I mean, my actual my PhD was in Manchester at Manchester Metropolitan, and it was a collaborative project between ManMet, University of Liverpool, and Oxford University. So one of the groups in Oxford, I knew them many moons ago. Unfortunately, it's quite a long time since I was on that project, but it's that was 12-15 years ago, and there were some collaborations sometimes, occasionally, which is nice to see. And yeah, I mean, that's really nice. So just really silly little story. You were talking about growing diamonds. So I used to make diamond-like carbon films, and one of the processes, basically I'd take carbon and I'd be using magnetron sputtering, and I'd be trying to influence what I grew, so the structure, which is exactly what you're talking about. I was trying to do it by changing the properties of the plasma, and where I was, I couldn't go and do all the SEM work myself or do all the various analytics. I had to get other people to do it, and I gave this person all my samples and said, can you measure them? And he gave them back to me, and he said, these ones are really good, they're really good sort of diamond. I was like, that's fantastic. He's like, yeah, they were almost there, and then I annealed them, and then I did this to them, and then I did that to them, and he processed all my samples, and it's like, no, I needed to know what they were.
So he annealed out everything you wanted to look at, or
all the samples that I gave him, he annealed them and then measured them. He was like, they were so close. So I did some.
Were they supposed to be annealed?
No. I wanted to know what I'd made. The whole point of my technique was what came out of the chamber, and have I managed to get towards diamond-like carbon? And he added these extra process. I still don't understand. That was a long time ago, and it was like. I mean,
you need to be so good at communicating when you're doing collaborative work, like this, especially because it's so easy to ruin a sample.
I just didn't understand.
The samples that we work on literally get sent across the country, and everyone has a different step on them.
Yeah.
And if you then drop the sample, or you put it in the wrong solution. Not saying I've done that, but I've seen it happen. And it's not just the sample's expensive, it's the hours of work that has gone into creating that sample.
Oh no, absolutely. I've lost samples, I've dropped samples.
It's almost like a rite of passage. You have to lose one, otherwise you'd just be too scared to ever do any work with your samples.
Absolutely. And I think once you've been in sort of the research side for a while, you know that equipment's going to break, and sometimes it's your fault, and sometimes it's just happened. You're going to drop a sample, you're going to lose a sample, you're going to measure something wrong. Like, you're going to set some equipment on fire, and maybe you're going to have a chemical release. Is that just me? Okay.
What have you set on fire in the lab?
One of our bits of equipment set on fire a couple of years ago. I got to use a fire extinguisher for real. Someone came into my...
for the positives.
Someone, I know, it was quite exciting. Someone came into my office and said, Clara, there's a fire. And I'm like...
They just walked in and were like, oh, the lab's on fire.
Yeah, I think the researcher that was doing the work and the person that came in, I think they were just so surprised. They weren't. I mean, I wasn't expecting it. I've been doing this for a long time, and I'd never seen deposition equipment just set on fire. I still can't quite explain it. Pardon?
You know what caused it?
It was in the height of summer. I think everything just got super, super, super hot. I think, which is quite remarkable. I mean, our deposition equipments are basically a bunch of steel and like some PTFE maybe. Like, there's nothing, there's no wood, there's no paper, it's not. And one of the things so someone walked in and said it's on fire, and I'm like, you're gonna put it out? And he went, oh.
Oh no, I've not had anything set on fire in the lab.
Oh no, that was a first. That was, I mean, I've been doing it for... Well, there were fires...
It's like being at school and someone that set the Bunsen burner off or something like that.
I did that.
Some paper in the Bunsen burner.
Oh, I did that. I was drying my hands on tissue paper, and it unravelled all along the desk. And it went... I was really scattered at school, but I think these days I'd have been like kicked out of class or something, but it was a different time. No, I worked for a company, and they were actually making... If you're making aluminium oxide and it's slightly substoichiometric, it's highly... It's likely to set on fire, basically. And the group that I did my PhD with, they were actually making pyrotechnic materials. So if you opened it and you opened it too fast, they'd set on fire. But then it was the coatings that would set on fire, not the equipment. The equipment was... That was a new one.
Did it ruin anything in the lab? Like, once you put it out, like, did any of the equipment get broken?
There were bits that we had to replace. So I said there was the PTFE sort of the ceramic spacers, the electrical spacers. They just melted. They just turned to carbon. So we had to replace them. But yeah, I think I still can't. That's the really annoying thing. Like, every so often this stuff happens, or it's because someone's done something ridiculous. This was just unlucky. I don't know. It was just bizarre. Still can't quite explain it. So go figure.
Now you're the laser safety officer.
Oh yeah. Well, I've not lost an eye with a laser yet. Yeah. I was just thinking that. Yeah. So you said that in your lab you're sort of spending a lot of the time measuring. You're spending a lot of time staring at the screen. Is that right? Are you able to do other stuff? Are you able to analyze what you've got afterwards? What?
Yes, obviously there's a lot of like kind of data analysis that you do post characterization and things like that. It's kind of inevitable, and also you don't want to measure like one incident. You'll do it like a number of times and amass like a set of data statistics on your sample to see how good or bad that sample is.
Yeah.
Essentially.
Oh,
there's a lot of like data processing, I think, science.
Oh, there is. Yeah. Yeah, there is, I think. But
and like, it's fitting your like data to a model as well.
Okay, yeah.
You might have to do. So at the moment I'm doing a lot of simulating, because I've been working from home for the last like few months.
Yeah.
So the labs have been closed. I've been trying to simulate like a micro field that I'd put my diamonds in to control that spin state. So I've been trying to like simulate what microfield I might get from certain circuit boards or certain like loops and things like that. That's been like quite like data heavy or like analysis heavy.
Okay, cool. But yeah, I think I was asking in a terrible way. But yeah, you're doing some simulation as well of circuits and trying
Yeah,
to change what you're doing, and you're designing the systems. You're not
yeah.
just measuring what you've got,
So
which
I
is
had
really
to, when I first started in Oxford, literally my first day, my supervisor was like, "For your optics, build your microscope." I had to work out how to build a microscope in my first term.
I
Um,
think that's a fantastic way of
so
doing it, though.
it's very hands on.
Yeah,
And luckily the group's amazing. So anytime you wanted help, you could just like ask one of the postdocs and they'd like come and help you. You
yeah,
do it. There was a lot of like knowledge in the group that I could benefit from when I started. Um, and we kind of maintain this kind of like teaching and help each other out in the group as we go as we've kind of gone on. But yeah, literally my first job was to build like a room temperature confocal microscope and then work
yeah.
out how to add like a microwave field and a magnetic field and work out a sample stage and all these things I had never like thought about. So I've moved lab twice now since
Oh
I've been
yeah,
in. I've had to rebuild the microscope every time we
yeah.
move lab as well. So it's gone under like a lot of iterations, but it means I know how everything works together. I'm very protective of my baby. Um,
Understandably.
yeah, it's been like I've learned like so much during my PhD. I've done so many different things that I hadn't expected because I even had to like write some of the software to control the hardware that we were using. I've done like some focus ion beam milling. I've done like sample cleaning and like so many different things. I think that's kind of what I wanted from my PhD to just
Yeah.
learn how to do all these different things and really not limit myself to what my project was, but to learn all these other things as well.
So that's what I love about material science. Like, and you said this at the beginning. There's so much engineering involved, and then there's the bits of chemistry because you've got to go into that, and then there's the physics side of it. I love that materials is a hybrid science. I mean, I think it's great, and you meet people that have such different backgrounds academically. And I know that I've got the engineering brain. I can build the equipment and put it together, but I don't necessarily have that chemistry knowledge or the physics knowledge. But that's why we have these groups, and you have that knowledge within the group. I just find it really interesting. So you said that you're writing up at the moment.
I'm supposed to be. It's not really.
You are writing up. It can seem slow.
It's slow. Yeah, I'm trying. I think like lockdown really like got in the way of me finishing up my experiments because I only had like a few months left of lab time, and then literally the pandemic happened and you weren't allowed to go anymore. Let's start writing up then instead without the rest of my data.
Yeah, unfortunately, so we just opened up our labs as well, and it's the people that are at the end, like you, we want to, if they do need to get any data in, then they need to get the data. I mean, it's always nice when you're sort of supervising to be able to say like you've got to stop going in the lab, and lockdown certainly did that. But unfortunately, there were some things that you still need to finish off. So, are you able to finish off those experiments now? Are you able
I
to
finished them off. I finished them off now. I just found work from home wasn't very productive during lockdown.
It's very difficult.
I think one thing to remember is that you weren't choosing to work from home. You weren't choosing to write at home. You had to be at home, and we couldn't go anywhere. We couldn't see anybody. We still really can't see anybody. And that was like really difficult, I think.
Yeah.
To make that comparison. And I don't know, I think it's interesting watching like academic Twitter. Some people are doing really well and publishing papers and starting postdocs. Some people are just like, I've done nothing for like 2 weeks.
Yeah.
I've like baked some banana bread and gone on a protest, and that's all I've done.
It's really difficult, and when you're writing, so during my writing, I was pretty much either going running or climbing every single day because I wanted to go out. But with the pandemic, it's not that easy. And it's not necessarily saying that you should be doing the exercise. It's just that I found it was really helpful to just get away from it for an hour, and it meant that I was able to be a lot more productive when I was writing. And you can't, like, you're in that same space. You're in the house. You're not you're not even going to the shops or going to the bar or whatever it is, the cinema. It's a different.
I think also really taught us how much like the choices we've made in our life and what like no one's suddenly chosen to live like this. We've all been forced to, and we're all just sort of like we're not doing it really doing it anymore, but we're all just like living at the extremes of our choices. Like I've chosen to live alone, but I don't want to be alone all the time. And I realised actually I don't really like being on my own all the time either. I much prefer like going into the lab. I much prefer like working in the office.
Yeah.
But I didn't really have that choice anymore. So the first year I loved it, but I actually didn't spend that much time on my own in my flat. I spent a lot of time in my department or like out.
Yeah. Yeah,
But I think it'll be so interesting on like science. I think it already has been interesting, and there's been like a lot of articles published about the kind of negative impact it's had, especially on women.
Yeah.
Lockdown, how like women publication records have like dropped significantly, but like men's have like stayed the same, if not increased.
Yeah.
And even just watching like how our groups developed over lockdown, like we've had new people start and they've not even met any of us in real life. They've started a PhD and been to the lab like one day and no one's even been in. Like it's just really strange. I don't know what the impact's going to be on our research.
It's hard, isn't it? Can I get some feedback? Yeah, no, it's hard. I mean, we had a postdoc arrive a week before we locked down, and I've still not, because I needed to get the equipment up and running, and then we need to test it's working and stuff like that. Like I've had to say to him, like, because I can't just have someone. Normally I'd be showing him and training him and stuff like that, but I can't do that now. It's difficult. It's a different way of doing science. I mean, so we were talking before, but you know, I've just, there was a lot of things that I wanted to do, and part of that was build up sort of YouTube videos and learn how to make them and how to do the science animations and all the other stuff. And so that's been great. It's like I've had the time to do that, but it is a change. It is a shift. There's no two ways about it.
Yeah.
And I mean, we're talking this week. The A levels came out in the UK. The A level results came out last week, and the whole, you know, who's going to be able to go to university, who's not. And then this week the GCSE results come out, and that's going to impact
tomorrow, right? They come out tomorrow.
Yeah.
Thursday.
And that's going to impact A level results, right? That's going to impact A level choices, and
even if it will impact university choices as well, because look at your GC results when you apply to universities as well, especially Russell Group ones.
Yeah, they probably do. Yeah.
GCSE results as well.
Yeah, I forget. I'm so long past that. I don't even know what my GCSEs were anymore. You get to a certain point where they're just. But
no one asks you anymore, so you don't really need to like remember.
Yeah, I still don't know if anyone at Oxford knows that I haven't got A levels. I actually don't have A levels.
A levels?
No, I never finished school.
But you have a PhD.
Yeah, I know. I never finished school. I just, my depression was really bad, so I dropped out. And so a few years later I actually did an access course, but I didn't finish that. And then I went back and I did a foundation course. So this is why we talk about foundation courses in Oxford. And I fully agree, because I was just going through a lot of problems in my life. And so A levels didn't work for me at the time. So I did a foundation, then I got onto a degree. I got my first class degree, then I worked in industry, then I got the PhD. So I like to show people that you don't necessarily have to have gone through the route, but I will say it's easier if you can. So
I think this is like a really important conversation to be having, that like currently the way education stands, it is failing a significant number of people.
Yeah.
And like there are so many different ways for people to like achieve like what they want. There doesn't need to be like one route to it, and not everyone has like the ability to like study for A levels at 18 and go to university at 18. And it's actually quite a privilege that you can, I think, in some respect. It's almost become like the the path you have to take is to go to university at 18. that doesn't work out for everybody. Like, not everyone wants to go to university at 18, 19. And I know my path was like really straightforward, but I kind of wish I'd done something a bit different. I've just been like at school or like at university for like forever, and I'll never leave. And I think it's the end of the PhD now, so I'm really just like, you know, getting a bit like tired of being in academia all the time. But yeah, I wish there was more discussions about other ways to learn skills and knowledge, and you could still be like in an academic research environment having not done a degree if you wanted to.
I know through my youth work, so I work with, you know, I run LGBTI plus youth groups, and there's so much bullying goes on that those kids just want to finish school. They don't care what grade they get. They just want to get out of school. And they're smart kids. And you talk to them about, you know, are you interested in university? It's like, no, I just want to get out. I just want to get out. And like I say, university is not for everyone. But I know that they're being failed by a school system where they're bullied and where the schools don't have the resources to help them. And so what do we do to make sure that they achieve their maximum potential afterwards? You know, we can't say that in universities we just take the people that have got these grades. And I get quite annoyed as well because I hear about the universities talking about increasing the number of people that come from state schools, which I think is fantastic. I agree with that 100%. But we forget that some people who go to the private schools go on bursaries. So I think I was looking at my old school. I went to my school, it's a private school. I went on a bursary. I would not have been able to go, and I think they said that something like 50% of their students are on bursaries. And so I hate to think that they're being discriminated against because they go to a private school. And within the school, it's probably the people with money that are going to, you know, be pushed by the school as it, you know. I mean, I know that there's a definite class divide in those schools because I was there. And so I feel like it's not just state schools. I think you have to look at more factors than that. And there's nothing wrong with someone from a private school, but from a working class, a council estate in the north of Manchester like me. Nothing's ever black and white. We shouldn't be saying, oh, nobody from private school, nobody from state school.
That was the massive issue of the algorithm that they chose to predict the A-level results. Because it was even people who were going to the same schools that were getting completely different A-level results.
Yeah.
As well, based on like where they lived and all these other things. Like, I probably should say this, but like when I was at A-level, my school invested in these like algorithm predicted A-level results.
Okay.
And I got like 2 grades higher than all of my predictions. And if I had got my predicted grades from the algorithm, I wouldn't have got into any of my universities. So I knew, like when they said this in March, I was like, not going to work out. I know what's going to happen. Like they really need to change the algorithm or just use the predicted grades the teachers gave them. It's really hard to capture all of that information because it's so complicated. I think you can't just give a computer all of this data, which is a limitation of computing in general. I think.
Yeah. No.
And expect it to like fit all of these possibilities, especially when the algorithm's written by biased people to begin with.
And we often hear about that with AI, right? I mean, there's certain things that slip in. Yeah. We say that computers aren't biased, but that's not. But the programmers are, unfortunately.
Programmers are, and the people like using that program are as well.
Yeah.
And it's really. Well, I'm not sure how hard it is to write unbiased program. I don't understand like a lot like programming, but there's been a lot of like papers written about how they need to change the entire structure of programming as it stands, I think, to make it more unbiased. I was really interested in hearing on like decolonizing computing, I think.
It's interesting how much of an impact there are, and so I think that's a really nice sort of segue because I mean, obviously, you've done a lot. You've been running WIMS, so the Women in Materials.
Yeah, Women in Materials.
And so you've put on a conference the last few years. Back when, do you remember when we could have conferences? Do you remember that?
I know. Actually, like I didn't because I was finishing my PhD. I didn't manage to organise like the conference this year. And then like when the pandemic happened, I kind of was like, I've got one thing less to do.
Well, this is it. The trouble is the people that are running these things are always the people that are super busy, and there's a lot of work. And it's true, actually. Sometimes it's like, because you want to do them and you need to do them, and you know they're important, but sometimes you need 5 minutes for you. So
it also got to the point where I really wasn't doing enough PhD work, and I think like, I don't want to say activist burnout because I'm not an activist, but like you can get burnt out doing all of these things, like, and it's so easy just to feel like so overwhelmed by the whole system and to get distracted by it, because the reason you're doing it is because you really, really care.
Yeah.
And then when like you don't have that support and you're not like taking care of yourself, it's so easy just to burn out and just not want to do anything at all in the end.
Yeah.
Maybe the lockdown was also good for that, all of us taking a break finally.
I know for me it came at a really good time. It meant that I had to stop sort of traveling around the country doing meetings. It meant that I wasn't going here and there, and I got to do a lot of stuff that I hadn't done for a while. Doesn't mean that I don't want to carry on. You know, I still want to do that stuff, but
I've been to so many great like Zoom conferences though, and like
that's good.
Online lectures and seminars, and things like that. They've been really good.
That's good. I've been with the Tigers in STEM group. There's been a series of physics talks, and I did one for the Institute of Physics as well. I don't know. I think you can definitely see people. You know, at the beginning, loads of people were tuning in, then people started tuning out because they were just at a bit of conference, and now it seems to be a little bit more up and down. I know that the LGBT seminar that I've gone to every year, we were supposed to be holding it at Oxford in January, so that's going to be an online event now. And I don't know how I feel about online events. It's great for webinars and seminars. Conferences, I'm not sure, because there's so much about in-person interaction in terms of the networking, but at the same time it means that they're more accessible for people who can't get there, who have maybe people with ME who just are too tired to go to a conference, or people who can't get on the train because trains don't have enough accessibility or whatever. So it's that's an interesting one. There's pros and cons, and this is why we need a hybrid system moving forward. This is why we need to be able to sort of, and I think that's one good thing about the pandemic, is that we've seen that we can use technology now.
Yeah.
And the truth is that it's only 2 years ago that I was at a conference and they had someone Skyping from America, and the sound was awful. It was a mess. But now things have really come on. So, yeah.
No, it's been great. And I've been to like a couple of online conferences, and I think the networking is always a bit of an issue.
Yeah.
But they've tried to be really creative, like having a Slack group or like a Twitter thing, or like, was it like I think IBM had like a Discord where they were teaching everyone how to use like the quantum computer that you could log into.
Oh, wow.
As well, which was quite cool. It was like 1,000 people could log on to like learn on Discord to like learn how to use the like quantum computer from IBM.
Oh, wow.
They had like a summer school, which I didn't go to, but like I heard it was really good. There's been some really creative like things happening using like tech that we have. And I've been to a lot of like networking drinks, which is a bit weird, on Zoom, but it's like you have these little breakout rooms and you have these like little conversations.
Yeah.
But I always find that one person ends up like chairing that conversation, even there's just 6 of you in a room.
Yeah.
Someone's like sharing like little room that you're in, so it's a bit weird.
Well, I'm curious for your feedback. We'll not do that here, but I'm curious in your feedback, because we've talked about similar things for the LGBT seminar, like how you do the networking aspect, and then do you have to have someone chairing it, because otherwise there might be no conversation, and you have to wait. It's weird. It's I'm not sure, and I've not been to any conferences. I guess I've just been going to webinars and seminars. I'm just saying letters at the minute. But
well, the APS March meeting went online like almost immediately.
Ah, okay.
And that was not a big conference. Like Proton 2020 is going to be like all online as well, and like a number of my group have had to pre-record their talk. Yeah. And then they're going to give like live Q&As as the talk's been like aired or whatever it's going to be.
Yeah, we've done that a couple of times, and I think it's kind of cool. Yeah, I did. I was doing a webinar for the Institute of Physics, and I lost my internet for about 40 seconds in the middle. I mean, these things just happen, right? These things happen. There's nothing you can do about it. But I knew that the audience sort of dropped while I was logged off, which is like, but it's yeah, I don't know. Yeah. So, but I mean, I realise we've been talking for 1:05, so I don't want to sort of keep you on here forever. But I mean, it's been really great working with you in terms of the equality and diversity work, and it gives me someone that I can sort of bounce ideas off or ask advice from.
Yeah, I'm so glad we met like so early into my PhD, and we could like work together quite a lot. I think it's really good to find allies really early on, or not even allies, as someone to like support you with what you're doing. Like, you've always been so supportive of like WIMS. You've spoken at like so many of our events, and even if like, I'm hoping WIMS gets rebranded soon. I feel like it's a bit exclusionary at the moment. But yeah, it's been like great to work with you.
That's interesting. I know you've said it seems exclusionary, but the trouble is that we still have issues with, getting women in physics, women in materials.
Yeah, I think my issue actually with like WIMS was that men felt uncomfortable coming to it. And when most of the department is men, like, we need your support. Like, we need you to come and listen to us and help us and tell us how you want us to be better as well.
Yeah.
It's not just about like women or,
Yeah. Yeah, no, it's difficult. And I realise we were talking before about how modern computer is binary and how quantum isn't and stuff like that, which is nice because, that's what we're trying to talk about when it comes to sex and gender as well. We're trying to get people past the binary.
I read a great book, and you need to read it as well, actually. You might have heard of it. It's called Life as a Unicorn. It's been written by Glam Rue. She's like a Muslim non-binary drag queen, and I think they're incredible.
Yeah, I know them. Yeah.
Yeah, he did a podcast recently with what's that presenter from Channel 4 called? I've forgotten his name. And he talks about like the non-binariness of sexuality and gender and quantum physics, and I was like, this is amazing. This is so good.
Yeah.
Their memoir is incredible.
Okay.
So good.
I've not read it. Yeah, they taught. They've done a few things. I think they did. Oh, I'm just rambling now. I'm sure they did something with the TEDx London group as well.
Oh yeah, maybe.
I think they did a talk. It wasn't the one that I was at, but I think they did a talk there. So, that group seems to be really on it. They're great organisers. They're really good. So, what we'll do, I mean, is there anything else that you feel that we've not talked about? We've talked about quite a lot of different stuff and we've wandered around quite a lot, but is there anything that you specifically want to talk about, whether it's diversity, whether it's quantum computing or anything? And if there's not, that's fine.
One thing that I do want to say that I don't think gets talked about enough is the responsibility of scientists to be talking about equality and diversity, and how you can make your research the most inclusive it needs to be. Yeah. Like I mentioned it earlier, how I hate using the word quantum supremacy, because it definitely has links to like white supremacy, and given that like a lot of quantum scientists are white men, I think that's something they should be questioning. And there was actually like an opinion piece that like I kind of signed my name to in Nature like a few months ago, or like last year now, about using the term like quantum advantage rather than quantum supremacy, and really looking at like the language that we use to talk about science and how we present our science, how we consider where our science sits in society. Like I already mentioned, who has access to quantum technology is going to be quite important, I think, in the future, and how that's used, whether it's like to help us or against us, and to always be critical of where your science sits within society. Because I feel like too often discussion is, oh, like science is elite, like it's pure, it's untouchable, like it's always going to be good. And actually, like, your science doesn't sit in a vacuum. It impacts everyone's life, like socially, politically, culturally as well. And I think that's something that a lot more scientists should remember. And I feel like very often when I try and talk about racism or sexism or like LGBTQI issues in science, it often gets like downplayed as not important and like, oh, it's side work, and it's work that we do unpaid anyway.
Yeah.
But it's still really important to consider those issues alongside your science as well. And like maybe like our science doesn't exactly have these really neat analogies to like racism or sexism, but it's still what we experience every day.
Yeah.
And I think that's really important to talk about as well.
It's amazing what a difference just being in a department where you know you can be yourself, for example. And I've been in groups where I didn't feel I could. I've been in other groups where I could have done, but I didn't realize that because I didn't see those signposts. I didn't see those little things. And so it's the little things really do impact your day-to-day in the lab.
Yeah.
And that impacts your science. It can't not do. I know that when my mental health was bad because of the things that I was worrying about, I wasn't writing papers. And yet, if I'd have felt more comfortable in the lab and I'd been able to talk about these things, then I would have been writing paper. I mean, I said that I didn't always have the best results, but I did have results, and some of them didn't get written about. And it's just like you say, just knowing that you're in a comfortable environment, just knowing that you feel the difference it makes, just feeling comfortable where you are, whether it's that you don't have to worry about outing yourself as gay, or that you're thinking, well, are these people laughing at my accent, or are these people
well, am I good enough because I'm a woman or because I'm a person of color, like, or am I not good enough because I've done this thing wrong? Like all this time you spend like second guessing yourself and having imposter syndrome about things that you have no control over. It's all like energy wasted, and it's all like inefficient uses of your time. But it's nothing that like you should have to like fix to make yourself feel better. They're all like in the environment that you work in. And
you can't help but have that imposter syndrome if you don't see anyone else like you around. You can't help but have those. That's just human nature. That's how the brain works. And so, of course, we need to try and address that. Of course, if we say we've got a welcoming group, we've got a welcoming department, then it needs to be actively welcoming. It's as simple as that. Yeah.
It's not enough just to write a statement or to have something on your website. You need to be living that and acting it every day.
Absolutely. I completely agree. I can 100% agree.
We've completely run out of time, but one thing I want to add on the back of that is I wish there were more discussions about mental health in academia.
Yeah.
Like there's just not enough. Like there's so many stresses on academics, and it leads to really poor mental health, and it's just like never discussed, like ever. I mean, I think now it's been discussed a little bit more, and since like lockdown it's been talked about a bit more, and like the whole like work-life balance is now in a discussion. But like that's a whole other conversation that would take like another hour to like record, I think.
No, but I still, we're not on a fixed time, but I think some of the things that we've talked about, like the pressure to publish, not being able to publish, all these things add to the work adds to your mental health. I mean, some people just have bad mental health, but a lot of times bad mental health is because of the climate in academia. And so we need to talk about it, and then we need to talk about, well, why are these people getting stressed? And then it's like, well, it's because of the climate, because we only get a year contract and a year contract and a year contract. It's because there's racism in the lab. It's because the pressure to have those papers, because we can't publish results that we've spent 6 months doing an experiment and there is a no result and we can't publish it. All these things add to poor mental health. So that's actually a really good point, and I'm glad you brought that up, so thank you so much. And
such a great conversation as always. It was very rambly, but I thought it was very us.
I think all of my conversations have been completely rambly. I mean, I've not chosen, but I've asked friends to do the chatting. So yeah, I think that's, I don't know. Hopefully there's some good science in there, and there's some good equality stuff in there. And then I think it's important because scientists are human beings, and if we keep on looking at the stereotype scientists, it's like, no, that's not who we are. That's not how we are. And doesn't mean that there aren't a lot of stuffy old professors out there in science, but some of us are real people too.
Even the stuffy professors are people too. They also have like feelings and home lives and things you might not know about them, and also doing science as well.
Yeah, no, you're absolutely right. No, you're right. should have thought about that. It's
but I do think there's this like impression in like the media or just like in society where like scientists are just seen as like untouchable and like just do the work all the time. We don't have lives and we don't have feelings or something, and we're just like robotic or something, and we're not. Like, we're just normal people.
I think that's not helped because there are a couple of sort of, say prominent scientists who they can do that. They're quite happy to just spend 24/7 working. They can do 4 hours sleep, and so they can publish papers, so they're successful, they get the grants, and they're on TV maybe, or they've got some sort of fame. We're not, and they're the people that are getting the spotlight as scientists. And like I say, it's because we're all different. So there's some people who can do that, but it doesn't mean that if you can't, that you're not a good scientist. It means that you do it differently.
Yeah, exactly.
And so we need to start showing, whether it's the way people work as well as other diversities, we've got to show that scientists are all different and there isn't one right way. So, yeah. Cool. All right. Well, with that, I'm going to wrap up. So thank you so much for
You're welcome. Thank you for having me.
Yeah.
It's so lovely to talk to you again.
I know. I can't believe it's been so long since we chatted. It's just, that's really sad. I miss people. I do miss people around the lab. So.
Are you in the lab tomorrow?
I am, yes.
I'm in on Friday.
Ah, right. Okay. Yeah, I'm in most days, but I'm trying to work from home on Friday. I'm in most days, but I'm trying to work from home on Fridays at the moment. But we'll arrange it. You've got a few. How much time have you got left in the lab?
A few months, like loads of time.
We got it. All right.
Yeah, I'll be around for a while.
Much. Yeah.
Don't worry.
Thank you so much. Thank you. All right, and with that, I'll cut to my outro. Cool. Well, that was awesome. I really enjoyed that conversation, as you can tell. Me and Shazeea are kind of friends, so but it's always great to learn some new stuff. So if you like that, like I say, I'll put her Twitter link below, and don't forget that I'll have mine down there. And also, if you want to like and subscribe, and we'll see you next time. Until then, bye bye.